Let us continue with the vector spaces from where we left and the video named part 1 of this playlist. In this video, I'm gonna discuss the dimension and basis of vector spaces. However, first I would like to develop the concept of dependent and independent elements of a vector space. In every vector space, there exists two different sets of elements. One set of element I would refer to as the first kind, and the other set of element I would refer to as the second kind. The elements of the set of first kind are quite independent of each other. That is, they cannot be expressed in terms of the rest and are therefore called independent elements. On the contrary, the elements of the set of second kind depends on each other. That is, they can be expressed in terms of different linear combinations of each other. In short, a vector space V can be split into two sets of elements. One set of elements is called independent elements and the other set of elements is called dependent elements. In order to understand this concept more deeply, I consider the linear combination of different elements of a vector space. For that, let me consider four elements u, v, w and x belongs to a vector space V. Then the linear combination of these elements over the space F is a relation of the form this, where the numbers a, b, c, d belongs to the field F. These numbers could be either the set of real numbers, the set of rational numbers, or the set of complex numbers. This relation says that the four elements u, v, w, x of the vector space V depends on each other through the numbers a, b, c, d belongs to the field F. That is, we can express any one of them in terms of the rest three elements of the space. I can rewrite this equation into this form, where 0 is now the element of the vector space V. If this equation is valid under a special condition over the numbers of the field F such that all of them are equal to 0, then that means that none of the four vectors can be expressed as a linear combination of the rest of the three, and therefore we say that this set of elements are quite independent of each other and therefore belong to the set of first kind. In order to pursue this concept a little more, let me consider the following three column matrices U, V and W, where each matrix is a 3-row column matrix. One can easily verify that these matrices obey the addition and multiplication operations. That is, we can prove that U plus V equals V plus U, and if C is a number over the field F and we multiply it with any of the three matrices, for example, I multiplied here it with U, then CU is again an element of the vector space, which qualifies these three elements to represent a vector space. Moreover, one can see from the structure of these matrices that none of them can be written as a linear combination of the rest of the two. So they constitute the set of independent elements of the vector space V. Now, we can use these matrices to construct any 3 rows column matrix of the space. For example, in the first case, I can construct an element A times U. That is again a column matrix, and where A belongs to F, so this matrix belongs to the space V. In the second example, I can construct a vector with first and third entry not equal to 0, that is A, 0 and C as a linear combination of the first multiplied with A and the third multiplied with C. And similarly, I can construct another column matrix with none of the entries equal to 0 as a linear combination of all those three matrices in the form of A, B, C, where A multiplies with the first column matrix, B multiplies with the second column matrix, and C multiplies with the third column matrix. So these three column matrices constitute the set of the first kind, where all the other matrices can be written through different linear combination of these three. Now one can easily verify that the three matrices X, Y, and Z that are constructed from different linear combination also obey the multiplication and addition rules. For example, one can easily show that X plus Y equals Y plus X, and similarly if C is a number belongs to the field F, multiplying C with Z will again reproduce a 3 rows column matrix which again belongs to the same space. Similarly, another very familiar example of the set of independent elements or the unit vectors of real vector space that I have been calling it the space of lines and arrowheads, that is I, J, K. They are independent of each other. We cannot express I as a linear combination of J and K, and the same is true for the rest too. Whereas all the other elements of the vector space can completely be expressed in terms of different linear combination of these three independent elements of the real vector space, that is the space of lines and arrowheads. To get a little more deeper into the concept of independent and dependent variable, I want to give an example from the space of 2 by 2 matrices. For this purpose, let me consider the set of these four 2 cross 2 matrices U, V, W, and X. So one can easily judge from the structure of these matrices that none of them can be expressed as a linear combination of the rest of three, and thus they constitute the set of independent elements of the 2 cross 2 square matrices space. However, different 2 cross 2 matrices with different entries at different position can be written in terms of the linear combination of these 4 matrices. So a complete set of all the vectors within the space of 2 cross 2 matrices can be expressed in terms of different linear combination of these matrices. And one example you see on the screen is this one, where a matrix A, B, C, D is just obtained through the linear combination of A multiplied with the first one, B multiplied with the second one, C multiplied with the third one, and D multiplied with the fourth independent elements. So with the concepts of dependent and independent elements, we can now go to define the basis and the dimension of a vector space. So the complete set of these linearly independent elements is in fact called the basis of a vector space. They are called bases because, as we saw previously, that every other element can be expressed through different linear combination of these independent elements. Now let me ask a question here. Is the set of elements constituting the basis of vector space is unique? That is there only one such set of independent elements for a vector space? The answer is no. Because in a vector space, different set of linearly independent elements exist. To see this, let me consider an example of vector space whose elements are 2 rows column matrices. Then one set of elements I can write in the form of these two rows column matrices. We can see from the structure of these matrices that they are linearly independent of each other. However, we can write any other 2 rows column matrix through different combinations of these 2 matrices. For example, I can write a matrix with entry A and B as a linear combination of A times the first element and B times the second element. Now consider another set of 2 rows column matrices in the form of U equals 1 and 1 and V equals 1, while the last entry being -1. Okay, we can see that these elements are also linearly independent from each other, and every other element of the space can be expressed from different linear combination of these two. For example, the above matrix with entries A and B can be expressed in the form of this linear combination of the two, where I multiplied A plus B divided by 2 with the first element and then adding it to the A minus B divided by 2 times the second elements. You can easily simplify that this addition is exactly equal to that side of the equation. This proves that a vector space can have different set of independent elements. However, the nature of the vector is quite independent from the structure of the basis vector. As we see in these two cases, we can obtain the same matrix through different combination of the two sets of elements. Can you think about a second set of independent elements for the space consists of 3 rows column matrices? The next important thing is to know about the dimension of a vector space. Well, that's quite easy. The maximum possible number of independent elements in the set of bases is called the dimension of a vector space. In the above examples of 2 rows column matrices, the dimension of the vector space is 2, whereas in the 3 rows column matrices, the dimension of the space is 3. On the other hand, in the case of 2 cross 2 square matrices, the dimension of the space is 4 because there are 4 independent elements in the set of bases. Just for the sake of reminiscence, the nature of the bases depend on the nature of the space. That is, whether the space deals with the square matrices, column matrices, or with functions. So accordingly, the basis takes the same form. Now, irrespective of the structure of the basis vector, it is customary to represent them by an alphabet with a subscript, where the subscript runs over the numbers of independent elements of the space. For example, we generally write it by E subscript I, where I runs from 1 to n, where n is the total number of elements in the set of bases. Then any element u is expressed as a linear combination of these basis vector, and we write it as sum over I equals ai ei, where ai is called the component of vector u along the basis vector ei. How can we extract the information of the component ai along the direction ei for a vector is the subject of my next video in this playlist. Stay tuned, and if you are picking, then wait for the next video.